This episode is brought to you by Brilliant.
We hope to one day send spaceships to distant stars and settle the worlds around them, but first, we have to find the systems and planets which are habitable. So today we'll be asking how we go about surveying the galaxy for places we might want to settle, or ensuring we have the information we need to best prepare any expeditions to the area. Now, principally, we tend to be thinking in terms of our telescopes back here on or around Earth, but we have three basic approaches for garnering information in the context of sending ships, and that's only one of them. If we can settle a system, that means we have ships to get people and gear there. So that also means we can get probes there for a flyby, or probes and scouts there for in-depth looks. Flybys represent their own category because of how spaceflight works. It takes immense energy to get a ship up to interstellar speeds, but the same energy is required to slow it down upon arrival, and even more energy to get that probe up to speed while also carrying its slowdown fuel. Thus, two identical probes, one doing a flyby and one traveling and halting a system, have different speeds. The flyby probe can move twice as fast as the one planning to stop, and that matters a lot when we're expecting centuries of flight time to even nearby star systems. The flyby probe can't get as much done in a given system, but it can get there faster, and it can probably carry several additional systems that allow for a wider variety of information to be collected. So we'll be arguing that each of those three categories should be done for any system: home astronomy, flyby, and protracted on-site surveying, and generally in that order. But we also need to be looking at several different ways to do each, and many of these will be complementary with each other too. Fundamentally, due to time constraints, we won't be able to do these probes in as much detail as I'd like today, so we will be giving them a deeper look in their own episode, Interstellar Probes, next month. But they still need to be part of the conversation for today, and we'll do those three categories: home astronomy, flybys, and protracted local scouting in order of operations as it were. So let's talk about astronomy first, then briefly discuss the flyby, and finally the scouting portions, which may also need a follow-up episode of their own. Now, I don't want to get too into the weeds on telescopes today, but basically we need to discuss what we're looking for ideally, what our telescopes can actually see, and what sort of strategy that implies. We also need to distinguish between looking for habitable systems, inhabited systems, and ones with technological life. Those last two both would have signatures, biosignatures, or technosignatures. And even if we decided we didn't want to colonize any world with life on it, a system showing biosignatures is obviously of interest for protracted study, but also indicates other planets in that system that might be good candidates for colonization. As an example, we wouldn't expect to find biosignatures around a system that had giant gamma-ray flares or novae any time in the last couple million years, but that's hard to spot astronomically. You might have some distant binary black hole partner that swung by and detonated as it picked up gas from the inner system, then meandered off for hundreds of thousands of years before returning for a repeat fireworks show. If it turns out that simple photosynthetic life evolves all the time and leaves oxygen-rich atmospheres, then systems lacking those biosignatures that otherwise look ideal for them suddenly become suspicious. And I'd use that term suspicious because when it comes to colonization and sending tens or even hundreds of thousands of folks on a colony mission, then these stars stop becoming a mundane catalog number and start becoming major investigations. We could almost see it as a hunt for a murder culprit for why a system is not inhabited, and the various causes being all murder weapons. You have big detective teams trying to figure out all the relevant colonization options from the data, and this is likely to be something comparable to a billion-dollar industry, with entire consulting firms of hundreds of experts analyzing data, mined by potentially thousands of massive telescopes and astronomical arrays. We're talking about something that amounts to the selling of an entire planet, or several, even if it's not actually a business transaction. The resources involved both in colonization and in its eventual development are staggering. So even a post-scarcity society able to send colony ships to places on a whim is not likely to skip or skimp on their initial homework and collecting of astronomical data. This data may still not be enough, but it's likely a colonization effort would be launched before a flyby had arrived. Indeed, since the flyby can travel faster, it might be launched at roughly the same time, and it might be that colony ships are sent with a primary target in mind, but a list of backups further out that they could divert to, all of which had flybys en route to them as well. Colony ships would need to carry some extra fuel to be able to change course a few degrees, and just generally need a lot more devoted to cargo and redundancy, so we should also be able to get non-flyby scout missions they are well ahead of the ship, even if they left at the same time, enough they might get a report back to the colony ship or fleet before they had to initiate their slowdown deceleration burn, and thus could divert to the next candidate with minimal fuel expenditure. There's also some low fuel options for turning around a star that they could employ with lots of advance notice. Now that has more to do with planning a colony mission, a topic that might make for a good episode on its own too, but it gives us an idea what our margins of error are, and it also tells us we don't really need to be ruling out 1 in 1,000 types of scenarios where we can't really tell till we get there with a flyby or even a Vanguard scout, because we probably can divert a colony fleet to the next decent candidate and can expect to have better and more detailed information as those other probes moving faster than the fleet arrive. Plus, it's likely that a fleet could arrive, stop, see it was a bad setup for a colony after all, refuel from local resources, and move on, possibly leaving interstellar infrastructure and outposts behind. Nonetheless, that represents years, if not decades, of lost time for settling folks who thought they were going to their future dream home in a pale shadow of it, so it goes without saying that maximum data is desirable back home before the ship launches. And of course, at the moment we're not even launching ships to distant stars, we still have a hard time launching telescopes to Earth's own orbital space. But as we contemplate the data we need to remember that we will also be able to put vastly more effective telescopes into play as we begin getting resources and infrastructure to launch interstellar missions. Currently, we're hunting for exoplanets that might be in the habitable zone of a star, and for stars that might actually have habitable zones. Many are pretty unstable and really aren't likely to offer any planets that are classically terraformable, as opposed to some of the more artificial and ambitious approaches to world building we often contemplate on the show, which can go nearly anywhere. What is a habitable zone and how do we find it? This one isn't too bad, as we're looking for a star whose output doesn't vary by more than maybe 10% for a period of several days during an observation period of as long as we can get. We need to know and calculate how much temperature variation in the context of the sunlight that a planet of a given size and composition could handle. There won't be any hard and fast criteria there either. A planet with a thick atmosphere and lots of greenhouse gases should be able to handle much more temperature variation, being more insulated, but probably also can't handle as much light overall because it is insulated and would get hotter. It might be able to handle a much more eccentric orbit around a star too, retaining heat when far from the star and heating more slowly as it neared perihelion. The simple version of a habitable zone is that it is where liquid water can exist on a world with an atmosphere that is neither too thick or thin to potentially be breathable, and it is always viewed as merely a quick approximation. It's a good guideline to see if a planet might have water or be able to hoard it if we can give it some. Can we see if a planet has water? Yes. In terms of the astronomical tells, water and ice both have albedos different from rock, as do water clouds from, say, the sulfuric acid clouds of Venus. It's also fairly easy to determine a planet's temperature by looking at the peak of its infrared emissions and watching them over the course of a year, along with the absorption spectra of that atmosphere. When we say year, mind you, we mean that planet's year, not ours, and that might be a few months for a habitable planet around an orange dwarf or bigger red dwarf, or multiple centuries for bigger stars like Alpha Pavonis, as we discussed in our episodes colonizing red dwarfs and colonizing giant stars. Every planet, indeed every object, including stars, emits radiation to the vacuum of space based on its temperature and size, and the wavelength of that radiation is determined by temperature. So once we get our eyes onto a given exoplanet, we can determine its diameter and average temperature simply from the infrared spectrum of that heat radiation. We can determine its day length just by watching how those emissions and those of reflected sunlight vary, assuming the board is not homogeneous of surface. If the whole surface is more or less the same rock, or one big ocean, or all frozen ice, this method doesn't work. But if it's got continents and oceans, then those each reflect light differently. The side of our planet covered almost entirely by the Pacific Ocean reflects and emits a much different spectrum than the side where most of the continents are, and we can determine day length by watching when they repeat. Ideally anyway. What's being reflected would alter a lot based on the weather, though that would average out over many observations, and at least tell us if it had an atmosphere of some sort. Also, the light it reflects is not what we get to see, we get to see what it reflects in our direction. And if we're looking at it from above or underneath its poles, then the daily change is a lot different than if we had an equatorial view. There is no guarantee its poles are perpendicular to its plane of rotation either, though due to how star systems and planets form, this will tend to be the case. But Venus orbits backward and Uranus on its side, and those make up 25% of the planets in the solar system, so that implies that's at best a guideline, not a rule. Regardless, anytime we're dealing with a planet whose day length is much smaller than its year length, we should be able to spot how long that day is fairly quickly just by the repetitions of patterns. As our telescopes improve, we might even be able to find larger moons around exoplanets from back here, and that not only helps with pinning down a planet's mass, but we can also look at how that moon's reflected light varies as a way of pinning down more of that planet's day. After all, Earth reflects sunlight quite brightly onto its moon, and also a lot of our weather and its astronomical telltales shift with the lunar month and tides. We don't necessarily need to know what the spectrum means, merely that it's periodic and what that period is, but generally these things all mean something, and one example of a biosignature, or candidate for one anyway, is lots of oxygen in the atmosphere. Unlike noble gases, which don't like to pair up on the chemical dance floor with anything, being snobby and aristocratic, oxygen is everybody's best friend, and pairs with or groups up with nearly everybody. As a result, it really shouldn't be hanging around in skies in great quantity unless something is releasing it, in favor of being sequestered into land and sea. The oceans, by mass, are 89% oxygen, and oxygen comprises 46% of the Earth's crust by mass. So basically all of Earth that's visible for astronomy is saturated with oxygen, 89% of the sea and 46% of the land. And ironically, the atmosphere is the least oxygen-rich part of our world's surface, being only 20 to 21% depending on the humidity. Most of that atmosphere is nitrogen, and yet nitrogen's crustal abundance on Earth is only about 300 parts per million, not even a thousandth of oxygen's abundance in the crust, and it is fairly minimal in the sea as well. Now, nitrogen is not a biosignature. Frosty Titan around distant Saturn has 94% nitrogen, and there is more nitrogen in Venus's boiling atmosphere than in Earth's, being only 3.5% of Venus's atmosphere, but that atmosphere being nearly 100 times more massive than Earth's. Rather, it's that free oxygen not bound to anything else that we view as the possible biosignature, because oxygen in molecular form is emitted by plant life and takes a long time to find something to bond with that is not already bonded. How do we know how much oxygen is floating around that sky? Well, oxygen is going to be coming in multiple formats, not just diatomic oxygen of 2 oxygen atoms, but also short-lived triatomic oxygen, what we call ozone, and various other short-lived molecules, also water, and here on Earth, nitrous oxide. Much as every object in space will have a characteristic blackbody emission of heat radiation, every molecular type has characteristic spectrums too. Now, nitrous oxide is principally emitted by the soil as part of the nitrogen cycle, and thus is another potential biosignature too, and one favored for super-Earths around cooler stars. Cooler stars meaning orange and red dwarfs, and those of course make up over 90% of all stars, and thus are most of our candidates for potential colonization, even if we like yellow dwarfs better, simply because of supply and demand. Now let me put a caveat on that. There are around 500 yellow or G-type stars within 100 light-years of Earth, and even if there are 20 times as many red dwarfs, those yellow stars are probably going to be one of the first places we launch colony ships to. Odds are good that we would be able to get a closer look at those red and orange dwarf stars from their yellow neighbors that we settled first. Nonetheless, Segura et al.'s 2005 paper, Biosignatures from Earth-like Planets Around M Dwarfs, or Red Dwarfs, highlights a lot of the basic biosignatures we would expect on planets orbiting these cooler stars. Methane, nitrous oxide, and chloromethane, also known as methyl chloride, were all labeled as good candidates as biosignatures, because they would have longer lifetimes and mixing ratios than on Earth or other worlds around hotter stars. Why? Well, mostly ultraviolet light. Bigger, hotter stars produce more of UV as part of their spectrum, and it tends to rip up molecules. Ozone, oxygen molecules composed of 3 oxygen atoms, is not stable and falls apart after around an hour, but constantly gets made in our atmosphere, as ultraviolet of roughly 200 nanometers can tear a diatomic oxygen molecule apart, and those 2 free oxygen atoms can find a new home. One of those might be a diatomic nitrogen molecule, creating N2O or nitrous oxide. Another is a diatomic oxygen molecule, which would make ozone. It can also be made by electrical disturbances, e.g. lightning, so don't think of it as only around the skies of planets around hotter stars, but it's also something that's destroyed by ultraviolet light, especially the nasty UVC range that's brutal on known life forms. Additionally, many other biosignatures would be destroyed by ultraviolet light too, and it's very hard to see an atmospheric biosignature unless it's in the upper atmosphere, so anything susceptible to rapid decay, especially from UV light, is a bad biosignature around hotter stars. What this means is that a reliable biosignature for one system isn't one on another, and things will be even more confused in binary systems with circumstellar planets orbiting stars with different characteristics. What we'll end up with is more of a checklist of possible things to hunt for on a given exoplanet in a given system, and that's for biosignatures, not simple habitability, which is also a very sliding scale depending on how far you're willing to go to terraform a planet. Technically, we don't even need a rocky planet to call a star system habitable, because a nice asteroid belt with the moons around a gas giant are potentially a lot more initially attractive to an inbound colonial fleet. As we detailed in our Life in a Space Colony series, when you spent the last century or two living inside a rotating habitat on a spaceship, embedding that in a nice icy asteroid or moon, and living there while you build others, and set up your interplanetary infrastructure is a lot more appealing choice than dumping your colonists down a deep gravity well onto a planet they'll need to spend centuries or millennia terraforming before they can walk around it without an environmental suit or under a dome. Now that said, a world is pretty habitable if we find it having a non-oxygen atmosphere and plenty of water, like Earth was back before the oxygen catastrophe circa 2 billion years ago, at least a billion years after life began on Earth. Oxygen is a waste product of plant life, at least Earth-based plant life, but initially it was getting sequestered by all the rock, and was what we would call a weakly reducing atmosphere, where oxidation is prevented or limited by the removal of oxygen and other oxidizing gases and vapors. The faint young sun paradox, with our sun being about 70% as bright back then, stars get hotter and brighter as they age, has still not been resolved. But we assume that back then the atmosphere was still mostly nitrogen, heavier in carbon dioxide, and also carbon and nitrogen bearing gases we see from volcanic activity. And we also assume way more methane, a great greenhouse gas, so as to allow Earth to have liquid water then, rather than just ice. I should note that the faint young sun paradox makes life on Venus early on more likely and ancient life on Mars less likely. It's a good example of how we might need to shift our entire view on finding habitable planets. Stars warm slowly, over billions of years, and we don't want to plan our colonization around such weights. However, at a fundamental level, the idea of looking for a world which is warm enough for life, but lacks the conditions to support it right now, is really only useful for finding existing worlds with life. We would not find an unoccupied planet that humans could live on from day one, because our living conditions are a byproduct of other life. Without life existing on a planet for a very long time, we will be unable to live on it outside of enclosed habitats. Once we start talking about changing a nice Earth-like world in temperature and gravity and possessing a nitrogen-rich atmosphere into one with more oxygen, then we need to acknowledge that it will be a slow process, and no easier, and indeed harder, than simply grinding up and smelting a few metal-rich asteroids into some big thin solar mirrors we can stick in an L1 halo orbit or Lagite position to heat a planet up, or a big solar shade to cool that planet down. Just for context, the bulk cost of 20 micron thick aluminum foil is about $2,400 a ton, and such a ton would cover 12,000 square meters of mirror surface, or shade surface, and could easily and fairly cheaply be reinforced with reflective Dyneema tape or similar. You might seriously alter a planet's thermodynamics with about 12 million square kilometers of the stuff, 1 billion tons of foil, which comes in at a considerable price tag of $2.4 trillion, which is comparable to about 5 months of US government spending. That's a lot of money, but not to buy a planet, so to speak. Amusingly, if you're setting up a space infrastructure for a planetary one, for interstellar colonists doing this backwards from us, the aluminum would be cheaper since on Earth, its cost would come mostly from the electricity needed to make it and the fuel needed to launch it. But with the right infrastructure, doing that in orbital space is much easier, where the sun is always shining. Or suns, you might be in a binary system after all. Thus, our whole concept for a habitable planet has to be both broadened and narrowed. Our odds of finding an oxygen-rich atmosphere on a world of oceans and continents with no life on it is pretty slim. However, our tools for terraforming make so many others viable. It really is more about what sort of mass the planet has, because even worlds baked free of all their water, or rather hydrogen, by being ultra-hot like Venus, can have large hydrogen beams aimed at the planet in conjunction with solar shades to cool its seas. Nonetheless, worlds which only need life on them to keep oxygen levels right are probably still the most appealing. We see those with cyanobacteria producing oxygen, but you can't just wait on that. Photosynthesis is a great oxygen producer, assuming you've got carbon dioxide and water readily available, as it will convert 6 molecules of each into a sugar molecule and 6 diatomic oxygen molecules. However, they use the same number of oxygen atoms to break that sugar down and use it. The estimates I've seen put the excess oxygen produced from this process at perhaps as low as 0.0001%. We actually don't have a good firm estimate of how much oxygen our biomass puts out per year, but it is on the order of low gigatons, and there's about 1.2 million gigatons of oxygen in our atmosphere. In the absence of animal life breathing in oxygen, we might see a rich cyanobacteria layer on a planet push out 1,000 gigatons of oxygen a year, but that seems optimistic, especially since we have no oxygen saturation already in place. See, as soon as the oxygen is created, the rocks and so forth on an unoxygenated world are going to oxidize and rust and largely absorb it. So I think even if transplanted or engineered cyanobacteria did amazingly well on a new world, then we're likely still talking a minimum timelines of millions of years to get an oxygen atmosphere. This instead implies using options like zapping out of existing water, ice, or rock, and sequestering things which would reabsorb that oxygen. Now, naturally speaking, we believe that, based on where banded iron deposits end in the geological record, that the Great Oxidation Event or catastrophe on Earth ended 1.85 billion years ago, and that banded iron peaked at about 2.5 billion years ago, and this oxidation of iron in our seas settled to its bottom, which we believe indicates the beginning of oxygen production by photosynthetic organisms in the Precambrian, and would seem to indicate that the natural timeline for oxygenating an atmosphere is on the order of hundreds of millions of years, though I could see shrinking it to much less. For looking for habitable systems though, finding worlds where this appeared to be in progress already would be a good biosignature, and also a good one for contemplating settlement of ourselves, depending on how we choose to view the life on that planet. That's a whole different problem, of course, but given that the first and very simple brain didn't evolve on Earth for over 1 billion years after the oxidation event ended, we are talking about incredibly simplistic life, and ones requiring relatively small ecosystems in terms of natural xenopreserves, or zoos. Critically, all these sorts of signatures are detectable most easily by atmospheric composition. Obviously, you have to spot the exoplanet first, but once we do, it's about building the right kind of telescope to hunt for a possible sign. You just have to decide if you're hunting for biosignatures or existing life, or signs a world is uninhabited and would be easy for us to inhabit. For gas dwarf planets, a type of super-Earth or mini-Neptune rich in hydrogen, we think that the James Webb Space Telescope could find ammonia signatures as possible biosignatures on those. For worlds around red dwarfs, as we mentioned, we can hunt for those biomarkers that ultraviolet light is unkind to, because that system has less of it. Looking for oxygen is obviously a good one for Earth analog planets, and there are many more that have been suggested, and again, every chemical we could find in an atmosphere is going to have an absorption or emission spectrum we can hunt for in the infrared, ultraviolet, or even visible range. Then it's just about building a big enough telescope up in space to stare at the candidate planets and realistically building many of them. Ultimately, I would not be surprised if a colonization-era humanity tended to commission a spectrum of telescopes for any new planet dubbed a possible candidate for colonization, focused only on that planet for years or decades. Indeed, given the value of different observational angles, it may be a large business for Oort cloud colonies in our system. Nonetheless, we begin to see the limit of astronomy and enter the realm of flyby probes that can get a real resolution on a planet and additional angle, and on-site missions in orbit of a planet or even down on it. We'll discuss those in more detail in the upcoming Interstellar Probes episode, but let's close today by briefly looking at each. We were talking about atmospheric biosignatures, and they are fairly limited, especially in telling us anything more than, say, the rough amount of biomass a world has that produces oxygen, which itself doesn't tell us much, and which to be honest is a real stretch to get. Outside of the realm of mega telescopes, which to be fair we might build even this century, the reality is that your resolution of an exoplanet from back here is 1 pixel. It is not an image, any more than a TV screen that's all white is an image. It is a light source though, and we can measure its brightness overall and its brightness in any given frequency. We can tell a lot by that, and probably some surprising things we haven't thought up yet, but there are real limits to it, and that's where flyby comes into play. As I was saying, when it comes to planets, or even entire stars, at best, our telescopes are only likely to see 1 pixel. Back when I was a graduate student running my college's observatory on Friday nights for public showings, something I often heard from folks, especially if we'd started by looking at our own neighboring planets, was how surprised they were that the stars were brighter through the telescope, but still just a little point, whereas the planets got wider and detailed. And that's because your eyes have pixels too, so to speak, and even nearby stars are still just a single bright pixel to us on all but the most enormous telescopes. Mars, at its closest, is still 10,000 times further away from us than it is wide, so it appears as a single point, unless we use a good pair of binoculars or a telescope, in which case we can see many pixels and its various features. However, nearby stars, even though far bigger than a planet, are so far away that we're talking distances to diameter ratios of millions even for closer ones, not thousands, and even more for tiny planets. A telescope able to see a planet like Earth around another star, as well as we can see Mars from Earth, would need to be 1,000,000 times more powerful. Now, as we discussed in mega telescopes, that is buildable. Same as we can build mirrors and shades big enough to cool entire planets, we can make telescopes in that scale. Indeed, we can make planets into telescopes, such as with the Kipping telescope, but all things considered, a flyby makes more sense much of the time. This need not be a tiny probe either. The key thing about these probes is that they can use the same fuel to go twice as fast as a ship designed to slow down at the end of the trip can. Early probes would be as small as we can build them and get useful equipment to another solar system intact and powerful enough to transmit home, maybe postage stamp sized ones like the Breakthrough Starshot initiative aims for, but later stage ones might be rather enormous, less like the Voyager probe in size and more like the Starship Voyager from Star Trek. As we'll see in our Interstellar Probes episode, even the early ones will likely be bigger than the Voyager probe. Now, much like astronomy from back home, there's likely to be a lot more data acquisition options and information we can pull from a flyby than at first we would suspect. For instance, some 100-ton space probe moving at 50% of light speed could have a handful of tungsten rods or needles that they could fire off to hit a planet, slowing the probe just a little and giving the rod a tiny kick, so that it arrived a few minutes or maybe days before the probe did its nearest flyby. Some 100-kilogram rod slamming into a planet at half of light speed is going to kick up a serious amount of debris. Indeed, more debris than a full-scale nuclear war on Earth could have, coming in around 14 or 15,000 megatons, 1,000,000 Hiroshima bombs. That's going to give you a nice amount of debris for accurately determining crustal composition. Now that's probably overdoing it, and you also might want 10 smaller ones hitting different spots, but that's an example of how a flyby probe can get some surface samples by blowing a cradle into the target and running spectrometry on the debris scattered by it. and that spectrometry might even be visible not just the probe, but the telescopes back home or on board a colony ship halfway there, who could verify with their own instrumentation. Now that colony ship, in truth, is not a good position to do much astronomy due to interstellar gas hitting at relativistic speeds. Indeed, they might launch flyby probes themselves, able to benefit from the ship's existing cruising velocity, especially as doing so would be free deceleration for them, and they would probably have to slow down more slowly than an unmanned probe would. See our Generation Ship series for more discussion of the problems in slowing down multi-kilometer long ships containing entire ecosystems. Astronomy is easier done to the side or behind the ship or probe, where all the relativistic dust is not slamming into it, and also big dishes and mirror arrays are limited to the normal size of the ship, since otherwise they give extra things for that gas and dust to hit, and the noise of all that is massive. With that in mind, they may opt to be sending unmanned probes or even manned scouts in smaller ships that maybe just departed when the main ship or fleet began to slow, and that didn't slow with the rest of the fleet, maintaining full velocity a while longer since they were able to slow faster. A big arc ship might be limited to a deceleration of 0.05 g to avoid problems for the ecologies in a spin gravity environment, and if they're coming down from 25% light speed, that means they need 5 years to come to a halt. Whereas a manned probe, able to handle a 1g burn, need not decelerate till it's 3 months out. And an unmanned probe, able to handle a 100g burn, could do it in a day, all using the same fuel. In theory, anyway. So that spaceship, 5 years out, or about 6/10 of a light year, could fire 2 unmanned probes out, each with the same fuel, but one accelerating with that fuel to do a flyby that would arrive almost 4 years before they did. An unmanned probe that will arrive more than 2 years ahead of them, potentially orbiting or landing, and a manned probe arriving a few months after that last unmanned probe with nearly 2 years to get work done. Indeed, if it is a fleet, then that might be an entire ship, and they might be very busy with projects in orbit, down on the ground, or even building large solar arrays near that star to both slow down the fleet and maybe incoming follow-up colony ships via Stellar, and to use that same array for terraforming efforts. Enormous star-powered energy beams have all sorts of handy applications, and that includes pushing other probes up to speed or sending on all or part of your fleet if the planet doesn't seem all it was cracked up to be and more people want to move on to other prospects. There is an awful lot more to say about surveying, let alone interstellar probes, and actually exploring alien planets, but we'll close out here for today, and as mentioned, we'll do that deeper dive on probes next month, and maybe also what life as a planetary explorer would be like after that. For now though, we have no interstellar probes or ships, just telescopes in orbit and here on the ground. But as we saw today, there is a lot we can do with those, and there's a lot more to determining if a planet is habitable than most folks realize. But when it comes to star systems themselves, with a bit of determination, ingenuity, and effort, there is no such thing as an uninhabitable star system. So as mentioned, we'll have our discussion of interstellar probes and explorers next month, and explore whether and when they are manned missions or robotic. But speaking of robots, let's leave the day with a puzzle from our friends over at Brilliant. We have a variety of robotic probes racing to a destination, codenamed Marv, Ray, Lex, Ty, and Mig, but they all got there on the graveyard shift when the coffee pot at the control center broke, so the notes from the night watch are a little vague, and we were trying to determine from their scribbled notes what order they arrived in. We were told that Marv arrived either second or fourth, while Ray arrived either first or last. Lex arrived third or fourth. Ty finished its journey quickly, either first or second, and Mig finished third or fifth. What order did the 5 arrive in? If you enjoy logic puzzles like that, there's a number of them over at Brilliant, and they are a great way to learn and to get the brain going for the day. The best learning is fun and interactive, challenging us, and math, logic, and science are often intimidating subjects for many folks, which is why Brilliant focuses on interactive learning for math, science, and computer science. Hands-on interactive learning is the best way to learn, whether it's advanced topics or more foundational ones like their new Everyday Math course, which provides a great new perspective on foundational math topics like percentages, fractions, and basic geometry. With Brilliant, you will be presented bite-sized pieces that you can learn at your own pace, when and where you want, on the go or in the comfort of home. To get started for free, visit brilliant.org/IsaacArthur or click on the link in the description, and the first 200 people will get 20% off Brilliant's annual premium subscription. So that will bring us to the end of our episode. We have a lot of great episodes coming up, starting next Thursday with a look at dark sky stations, stratospheric satellites, and ultra-low orbital infrastructure. Then we'll jump into June and start the month by asking what ancestral simulations are and if we are living inside one. Then it's time for our return to, and expansion of, our original episode looking at all the various giant structures humanity might one day build, with the Megastructural Compendium, which has an approximate runtime of just under 2 hours, making it our longest episode ever, so that we can cover every megastructure we know of, which is around 100 major types. Definitely an episode you'll want a drink and a snack for on Thursday, June 9th. Then we'll have our next Sci-Fi Sunday here on SFIA on Sunday, June 12th, for a look at the Silurian hypothesis, the concept that some ancient civilizations, like intelligent dinosaurs, might once have dwelt on Earth long ago. We'll also ask what would remain of humanity's accomplishments millions of years from now if we suddenly died off. As a reminder, this month's livestream will still be on Sunday, May 29th at 4 p.m. Eastern Time, but instead I'll be giving a live talk from the International Space Development Conference in Arlington, Virginia. Now, if you want alerts when events and episodes are coming out, make sure to subscribe to the channel and hit the notification bell. And if you enjoyed this episode, please hit the like button, share it with others, and leave a comment below. You can also join the conversation on any of our social media forums, find out audio-only versions of the show, or donate to help support future episodes. And all those options and more are listed in links in the episode description. Until next time, thanks for watching and have a great week.